Every year, over 100 million cubic meters of plywood are produced worldwide. That's enough to cover every roof in the United States with a whole tree. But few people know how this journey actually begins. Imagine, a wet log, still smelling of the forest, enters steaming chambers, passes through steam, knives, fire, and a pressure of 250 psi to become a wall, a roof, or even a stage. How is a log transformed into plywood that will last for decades? And what secret does the peeling process hide? If you watch until the end, you'll discover what they don't write in textbooks. The factory wakes up before dawn. With a deep roar, the gates open and trucks with freshly cut logs slowly drive onto the site. You should see them. Oaks, pines, poplars, true forest giants, long, thick, heavy, with wet bark and the aroma of a freshly felled forest. The wood is still breathing, still warm from the sun that shone on it for the last time. And so it begins. The logs are dumped onto a hydraulic feeder, where they move like logs in a mountain stream. Only instead of water, a system of rollers and chains is at work, and instead of a river, washing chambers, loud and ruthless. Bam! A jet of water under a pressure of 1000 psi, almost like a fire hose, hits the wood from all sides. All the mud, dust, and pieces of bark are torn off, like old skin. The logs spin, collide, foam, and hum. It looks as if the wood is undergoing a purification ritual before becoming something greater. After such a washing, they shine. But that's not enough. The wood is strong, rigid. You can't peel it like butter. So next, the steam chamber, a real wooden spa resort, but on an industrial scale. The logs drive onto an overhead crane, are lifted, and slowly submerged into giant cylinders, steam vats 60 feet long. And there, behind closed steel doors, begins what engineers call fiber softening. But I would call it wood stewing. Inside, it's 220 degrees Fahrenheit. The steam is thick, saturated. For 8 or even 12 hours, the logs soak in this environment. The steam penetrates to the core, the fibers relax, the resin starts to flow a little. And if you listen closely, it's as if you can hear the wood sigh, as if admitting, "Okay, I'm ready, make me into plywood, make me." They are taken out, and the logs are no longer the same. If at first they crackled with tension, now they are flexible, elastic like wet towels. Steam still billows from the bark, wood chips remain on the floor. The smell is like a sauna in the forest after a rain. They are stacked on roller conveyors and prepared for the next step, peeling, where they will lose their wooden identity, but acquire a new one. The log, fresh from the steam bath, is still smoking, as if someone just threw it from a pot onto the cold concrete. It is grabbed by a mechanical clamp, huge like a transformer's paw, and lifted to the peeling machine. A giant with a steel mouth that is already humming, like a Harley-Davidson's engine at full throttle. This machine is a centrifugal peeling line, or simply put, a shredder. The log, heated and pliable, is mounted at the center of rotation, like a kebab on a skewer. It begins to spin slowly, then faster, even faster. And here the peeling knife comes into play, long, straight like a samurai sword, only made of steel and as wide as the entire log, 4 or 5 feet. And it doesn't cut, it peels, layer by layer, strip by strip. Screech! Shh! Vroom! The log spins, and a thin, flexible layer of wood comes off it, only 1/16 of an inch thick. It unfurls like a gift wrap ribbon, only instead of glitter, there's warmth, steam, and the smell of fresh wood. And instead of music, the roar of hydraulics and the rhythmic rustle of the plywood roll. This ribbon is veneer, the basis of plywood, its soul. It comes out without stopping, tens, sometimes hundreds of feet long, is rolled up or automatically cut into large sheets, typically 4 by 8 feet. Peeling is a sensitive process. The log must be straight, symmetrical, moist, but not too soft. If it cracks, it's over. The veneer will have holes or waves, and the plywood won't be grade A, but oh no. Operators carefully monitor every movement. On the display, graphs of speed, pressure, layer thickness. Cameras capture every knot. If something goes wrong somewhere, the machine stops in a second. And then they fix it, readjust it, and back to the fight. When the log is exhausted to the core, what remains is a core, a few inches thick. It's automatically ejected to the side, to be later processed into sawdust, fuel, or wood chips. Nothing is wasted here. Everything will be used. And the veneer sheets, hot, pliable, still smelling of steam, race onto the dryer. But for a moment, as they come off the knife, they are incredible. This is living wood, which has already lost its tree form, but has not yet become plywood. It flows like water from a tree. It dances like a gymnast's ribbon. It rustles like paper, but carries the strength of a trunk. As soon as the veneer ribbons come off the knife, they are still damp, steaming, like leaves after a thunderstorm. And so, they are picked up by an automaton, pulled into a drying line, incredibly long, like a train in Texas. Inside, hot air, about 200 degrees Fahrenheit. Flows are accelerated by fans. The sheets race along a conveyor belt at a set speed. 10 or 15 minutes, and the veneer comes out dry as a bone. And at the same time, still flexible, because if you over-dry it, it will break like a chip. And if you under-dry it, the resin won't stick later. Everything, down to the micron, down to the second. It's not just automation at work here, but also the intuition of the dryer operator, who can tell by sound and smell. This oak is still damp. Next, sorting. Veneer sheets, dozens, hundreds, roll onto an inspection platform, where operators or modern cameras with artificial intelligence decide where each should go. A sheet without knots, perfectly even, goes for the face layer, the highest grade. With small cracks to the middle, with large defects into the inner layers, or for backing. Everything that doesn't fit is shredded and sent for recycling. Nothing goes to waste. The selected sheets are fed to glue applicators, huge drums that evenly roll on a waterproof phenol-formaldehyde resin. It's dark brown, thick, sticky, smells sharp, like a school desk after woodshop class. And here, everything is important. The layer of glue, the temperature of the sheet, the direction of the fibers. Because plywood isn't just glued sheets, it's cross-laminated layers, where each layer runs perpendicular to the previous one. This is how it gets its mechanical strength, flexibility, and resistance to warping, like a bulletproof vest, but made of wood. The finished sandwiches of several layers are placed in a giant hydraulic press that applies pressure from 150 to 250 psi at a temperature of about 300 degrees Fahrenheit. Inside the press, it's hell, but a controlled one. 10 minutes and the resin hardens, binding the fibers into a single body. The plywood becomes monolithic, hard, sanded from the inside out. This moment is the culmination of the entire process. Here, from wood and glue, a plywood sheet is born, ready for battle. Coming out of the press, the sheet is still hot. It is laid on a cooling conveyor, a wind tunnel where cold air draws off the residual heat. Then, a sanding machine. On both sides, large rollers with sandpaper remove microns of irregularities, even out the surface, remove excess glue. Next, cutting into standard formats, usually 4 by 8 feet, although a customer can request 6 by 10 feet, or even mini sheets. Then, quality control, scanning, marking, packaging. Each sheet is marked with a code, a grade stamp, a production date. It is packed in stacks of 40 to 60 pieces, wrapped in stretch film, and off to the warehouses. Each sheet that leaves the factory has passed through water, steam, blades, fire, a press, and saws. And now it can be anything. It becomes a wall in a new house in Kansas, or the back of a chair in a New York coffee shop. Sometimes, the level of a stage in a music school in Iowa. Another time, the roof of a house in Mississippi, the floor of a trailer somewhere in the middle of Arizona, or even the body of a truck speeding down I-80 at night. And each time, thousands of layers of wood hold together, as if whispering, "We are plywood. We are stronger than we look." What made of plywood is right next to you right now? Every year, over 50,000 tons of uranium are mined worldwide. But to get just a few grams of energy from it, you have to move mountains. It all starts in the desert, where the temperature reaches 100 degrees and ends in a reactor that powers New York. Here, centrifuges that spin faster than an airplane turbine, and substances that corrode metal in seconds. But the most interesting part is what even safety instructions don't talk about. Watch until the end, and you'll discover a secret that will change your perception of nuclear energy. It all begins in the dust. And that's not figuratively speaking. Uranium ore is mined in hot regions: Arizona, Wyoming, Texas, New Mexico. Sort of like cowboy landscapes, only instead of lassos, there are drilling rigs, and instead of a sheriff, engineers in anti-radiation suits. The sun here is scorching, up to 100 degrees Fahrenheit in the shade, if you can find any. There are two ways of mining: open pit, where the top layer of soil is removed and the ore is pulled out by excavators, and underground mining, with explosives, lifts, and ventilation that howls like an old tractor. And there's also the in situ leaching method. Pipes are driven into the ground, and special solutions are pumped in to wash out the uranium directly from the rock, and then it's pumped back out. All this ore, a grayish-brown rock, looks no different from ordinary stones. But in it, uranium-235 is only 0.7%. The rest is almost useless mass that doesn't work in a reactor. And to squeeze the needed drop of energy from it, you have to process hundreds of tons. That's why they say nuclear energy is quite a marathon. After mining, the ore is crushed, ground, and thrown into a chemical bath. Acid or alkaline solutions are added to extract the uranium, like coffee from a filter. Then, filtration, precipitation, drying at 500 degrees Fahrenheit. And at the output, yellowcake, a yellow powdery concentrate. The official name is natural uranium concentrate, but everyone at the plants just calls it yellowcake. It looks beautiful, mustard-colored, fluffy, like a spicy powder for barbecue. But God forbid you inhale or touch it. Alpha radiation, a long half-life, dangerous dust that penetrates the lungs and settles there forever. People work with it only in respirators, suits, behind 3 layers of glass protection. Yellowcake is packed into double-walled barrels, loaded onto trailers with an escort, and wrapped with radiation signs. And off it goes to the enrichment plant. It's from this poisonous dust that the journey begins, leading to the white light of a lamp over a kitchen table, or the electricity in the subway rushing under New York. Well then, yellowcake is here, in barrels, radioactive and dry as a desert wind. The next step, turning it into a gas. And not just any lavender-scented gas, but uranium hexafluoride, the very same from which the required isotope for reactors and more is later separated. Let's cook, baby! The uranium concentrate is first dissolved in acid, purified, filtered from impurities, and converted into uranium dioxide. And here the magic begins. Uranium dioxide is treated with fluorine in special reactors at a temperature of 1000 degrees Fahrenheit. And as a result of the reaction, a volatile, transparent gas is formed, which boils at 133 degrees Fahrenheit. That is, you just need to heat it a little, and it turns from crystals into vapor. But it's not that simple. It is extremely toxic. It corrodes metals, destroys skin, and in humid air, it immediately turns into hydrogen fluoride and uranic acid. That is, a deadly cocktail. That's why all this is done in sealed, automated reactors that look more like devices from a villain's laboratory. Temperature, pressure, ventilation, everything is under control. Workers sit behind thick windows, monitoring the sensors. Any mistake, boom, or hiss, and you're already in a hazmat suit, scratching your heels on the way to the shower. This substance forms as solid whitish crystals when cooled to room temperature. These crystals are stored in steel containers, barrels with engravings, a batch number, and a radioactive sign. Each one weighs under 14 tons. And so, mission accomplished. The dust is turned into gas, ready for the most interesting part: isotope enrichment. But don't rush to celebrate. This gas is like a wild cobra. Beautiful, shiny, but if it bites, no one can save you. You think spinning a washing machine is fast? You haven't seen nuclear centrifuges that do 70,000 revolutions per minute. That's 10 times faster than an airplane turbine. And all for one thing: to separate uranium isotopes. The fluorine-enriched uranium dioxide, that same poisonous gas we just made, is pumped into a tall, narrow cylindrical chamber, which is spun up to an insane speed. Centrifugal force does its thing. The heavier U-238 atoms fly to the edge, while the lighter U-235 atoms stay closer to the center. A tiny, microscopic difference, 1% in mass, and all this explosive technology spins just for it. But one centrifuge is not enough, so they are connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas, then passes it to the next. And so cycle after cycle, until the U-235 content becomes at least 3 or 5%. This is the reactor standard. For weapons, of course, completely different routes are taken. They are classified and under strict international control. Okay, the gas is enriched, but in its gaseous state, it won't feed a reactor. So now it's converted again, this time into a solid ceramic form. After a series of chemical reactions with hydrogen, oxygen, and ammonia, the gas becomes uranium dioxide, a solid substance with a dark gray color. This powder is pressed under a pressure of 20 tons into small cylindrical pellets with a diameter of 3/10 of an inch. They look almost cute. But each such pill is like a charge of energy equivalent to 17,000 cubic feet of natural gas. Next, the pellets are sintered in furnaces at almost 3,000 degrees Fahrenheit to make them strong, like porcelain. Then they are polished, ground. Perfect dimensions are important for a tight fit in the cladding. The pellets are placed in long metal tubes, fuel rods, usually made of a zirconium alloy, because it doesn't rust, doesn't react with water, and withstands insane radiation. Over 300 pellets are placed in each rod. The rods are hermetically welded and combined into modules, fuel assemblies. They look like a frame of several dozen tubes, assembled in a square. One such assembly can weigh over 1,500 pounds and works for up to 6 years in a reactor. After assembly, testing for leaks, uniformity of filling, weld integrity, behavior under temperature. There are no trifles, because each of them can cost not just money, but lives. The finished fuel is packed in armored containers that can withstand impacts, fire, and falls from a height. Transportation is under guard on a special route with an escort, GPS, and mandatory. 2 seals, 3 codes, and a dosimeter on each side. Because even in its peaceful form, this is a dangerous thing that commands respect. After all this, what remains is depleted uranium hexafluoride. They call it tails. It's a mixture of isotopes where there's still a bit of uranium-235, but not much. These tails are stored in steel drums on special sites under supervision. But in the future, they can be reprocessed in new generation reactors, where everything will be squeezed out to the last drop. When a fuel assembly has served its 4 or 6 years in the heart of a reactor, it's no longer the shiny star it was at launch. It is removed, carefully, with a robotic system, and moved to pools of water. The depth is over 20 feet. The water cools and shields the radiation because the fuel is still hot, physically and radioactively. There it rests for several years. Then, 2 paths. Either long-term dry storage in concrete containers with double walls, or reprocessing. In other countries, because the US mostly stores rather than reprocesses. In dry storage, the cassettes stand for decades, cooled by natural ventilation, as if in a nuclear monastery. This is not the end, but a new stage of life. Slow, controlled, but deeply connected to the future of energy. Because even after the reactor, this fuel remains a source of heat, a lesson, and a reason for respect. Every hour, over 3,000 miles of electrical cables are laid worldwide. But few people know that this involves gigantic metal spools, each one an engineering marvel weighing over 20 tons. Their diameter can reach 33 feet, and inside, up to 37 miles of wire capable of transmitting hundreds of thousands of volts. A half-inch error, and everything goes down the drain in losses. How are these steel giants created with precision down to 1/100th of an inch? And why can't any power transmission line exist without them? Watch, and you'll be amazed. This story begins with calculations. Before the first bolt touches the steel, a team of engineers dives into mathematical alchemy. Each spool for a high-voltage power transmission line is created for a specific type of cable, so there are no trifles here. Blueprints, models, and calculations come into play. It is necessary to consider the outer diameter of the cable, for example, 2 inches. Its weight, which can exceed 3 pounds per foot. Density, number of turns, winding angle, and even the insulation's coefficient of friction. On average, up to 6 miles of cable are wound onto one spool. That's almost 32,000 feet of heavy, multi-insulated wire that, under voltage, can carry hundreds of thousands of volts. An error of just half an inch in the spool's diameter, and the cable might start coiling incorrectly, shifting, compressing, overheating. In the worst case, it gets damaged even before installation. And that's tens of thousands of dollars in losses before even starting. Moreover, the core diameter of the spool can reach 5 or 6 feet, and the total diameter of the flanges up to 33 feet. The weight of the structure exceeds 40,000 pounds. That's like 2 large SUVs screwed together and stood upright. And this entire mass has to rotate smoothly, without misalignment or vibrations. Are you impressed? Because I sure am. To avoid disasters, engineers add a coefficient of material expansion. As metal changes size when heated, consider transport weather conditions, and also the winding geometry, because even too steep a winding angle can damage the cable when it's unwound. When the drawings are approved, giant workshops come onto the scene, hangars the size of a football field. Here, metal flanges, cores, and frames appear. Most often, the spools are made of steel. It's steel that can withstand the weight of the cable and the loads during transport. For an average spool, more than 2 tons of steel are needed at the laying site. So, each giant spool for power transmission lines starts with cold metal, thick steel sheets that arrive at the factory as plates measuring 6 by 12 feet or more. Their thickness ranges from half an inch to 1 inch, and this steel is structural. Strong, tough, capable of withstanding high loads without cracking or deforming. First, the sheets are fed to plasma or laser cutting machines, which are programmed according to precise drawings. A giant plotter, emitting a hot beam, literally burns complex shapes into the metal. These machines operate with an accuracy of 1/100th of an inch. Such precision isn't for beauty's sake, it's critical. Because even the slightest error on one flange can cause the spool to lead the cable off-center during rotation. And that's a risk of misalignment, jamming, and failure during installation. The discs for the flanges are cut in pairs, identical rings 20 to 33 feet in diameter, with holes for connecting bolts. Technical slots and markings for future reinforcing elements are made on the surface right away. After cutting, they are processed by grinding machines. Burrs are removed, and they are prepared for welding. At the center of the future spool is the core, a large steel pipe that will serve as the drum for winding the cable. Usually, its diameter is from 5 to 8 feet, and its length up to 10 or 16 feet. The pipe is cut from thick wooled rolled stock and reinforced with stiffening ribs inside. These are thick steel strips that form a frame and prevent the pipe from sagging under the weight of the cable. After all the parts of the future spool are cut, the stage where every millimeter matters begins: welding and assembly. Here, metal geometry transitions from 2-dimensional to 3-dimensional. 2 giant flanges are attached to both sides of the core, a steel pipe that will hold tens of thousands of feet of heavy cable. The entire structure must withstand not only its own weight, but also dynamic loads during rotation and transport. Welding is done manually or automatically, depending on the size and complexity. Most often, submerged arc welding is used, which allows for creating dense, strong seams without voids. The joints are additionally ground, as any protrusion or unevenness can damage the cable during winding. Then, reinforcement. Stiffening ribs, which are thick steel plates placed inside the core and at the joints with the flanges, are added to the structure. They prevent deformation under pressure. To fix all the parts, bolts up to 1.5 inches in diameter are used, tightened with special hydraulic torque wrenches. One such bolt can withstand a load of tens of thousands of pounds. The finished spool is installed on a temporary axle and rotated. Engineers check the balance using a laser level, ensuring that during rotation, no part shifts even a quarter of an inch. If the structure wobbles, it's ground, adjusted, and sometimes parts of the elements are reassembled. And only after this is the spool considered ready for the final stage: anti-corrosion treatment, painting, and testing. The finished spool has just been removed from the rotating stand after welding. It's still warm, smells of metal and ozone, and its surface is covered with dark gray spots. That's scale. It looks like a thin crust, similar to coal dust, and remains after the metal comes into contact with high temperature. Along with it, small remnants of oil, dust from grinding, handprints. Painting in this state is a waste of time. The coating won't stick, it will peel off in the first few months. So first, mechanical cleaning takes place. The workshop buzzes with tools. Workers with stiff brushes on grinding machines go over the joints, flanges, and stiffening ribs. They remove rough irregularities, clean the seams of residual slag. But this is not enough. Next, a sandblasting unit comes into play. A large chamber, or just a separate section in the workshop. The spool is brought inside on a special platform. Then, the roar of a compressor and a stream of fine abrasive starts hitting the steel surface under high pressure. Sometimes quartz sand, sometimes steel balls. It sounds like a storm of hail hitting tin. The surface changes before your eyes. Where there was just dark mottling, now there is an even, matte gray metal with a slight roughness. If you run your finger over it, you feel not smooth, but slightly velvety to the touch. This is exactly what's needed, because this micro roughness significantly improves adhesion with the anti-corrosion primer. In chemistry, this is called the anchor profile effect. When the treatment is complete, the entire surface is blown with air, blowing out residual abrasive from corners and crevices. This is the perfect moment to apply an anti-corrosion primer, the first protective barrier between the metal and the environment. A worker in a mask and protective suit takes a sprayer with a thick gray liquid, a zinc-rich primer. With each press of the trigger, a thin, even mist comes out of the nozzle, settling on the surface. The zinc in the primer acts as a sacrificial metal. It is the first to react with moisture, saving the steel from corrosion. After a few minutes, the spool is already covered with a thin, almost invisible layer. It looks a little lighter, as if dusted. In a few hours, this primer will polymerize and form a chemically resistant film that is firmly bonded to the metal. It is this layer that takes the first hit from time, moisture, and temperatures. For export or harsh climatic zones, additional layers may be applied. Marine varnish, hydrophobic films, or even heat-resistant coatings that can withstand heating up to 300 degrees Fahrenheit. When the coating dries, the spool is carefully inspected. Under ultraviolet light, all microcracks, bubbles, or gaps in the layer are visible. If there are doubts, an electric spark test is performed. A special probe glides over the surface, and a spark jumps only where the insulation is compromised. This ensures that every inch of metal is reliably protected and will withstand years of operation in any conditions. Every year, billions of dollars are spent worldwide on developing military technologies. But only one aircraft has become a true ghost in the sky, as invisible as death itself. Its creation cost over $23 billion, united more than 40,000 people from 46 states, and even required the construction of a new industrial city. If you found out what is hidden under its black coating, you would never look at aviation the same way again. Does your country participate in the production of components for military aviation? Let us know in the comments. The design of the B-2 Spirit strategic bomber began in 1979, when the Cold War was reaching its peak. It was then that the US Department of Defense initiated the Advanced Technology Bomber program, with the goal of creating a new generation aircraft capable of penetrating the most advanced Soviet air defense systems while remaining invisible to radars and delivering nuclear or conventional weapons over intercontinental distances. Leading American aerospace corporations participated in the competition: Northrop, Boeing, Lockheed, Rockwell. After a lengthy stage of development and testing, in October 1971, the Northrop-Boeing consortium was declared the winner. It was their project that received the designation B-2 and the name Spirit. Unlike previous strategic bombers, the B-2 was built on a unique flying wing design, which provided minimal radar cross-section and significantly better flight technical characteristics. In the mid-1980s, the B-2's design had to be significantly changed. The mission profile was adapted for low-altitude flights with terrain following, which allowed for even more effective penetration of Soviet air defenses. This led to a 2-year delay in the first flight and a $1 billion increase in the program's cost. By 1989, about $23 billion had been spent on the B-2's development, and even specialists from the Massachusetts Institute of Technology were involved in the work, assessing the aircraft's effectiveness under conditions of strict secrecy. The first public showing of the B-2 Spirit took place on November 22, 1988, at Plant 42 in Palmdale, California, which is where it was assembled. The first flight of the B-2 took place on July 17, 1989. Initially, the US Air Force planned to order 132 aircraft, but after the end of the Cold War and the collapse of the USSR, as well as due to the extremely high cost, the series was reduced first to 75 and then to 21 units, including a prototype, 5 pre-production, and 15 production machines. Almost all B-2s received their own names in honor of American states, emphasizing their uniqueness and symbolic significance for the country. Thus, the B-2 Spirit became not only a technological breakthrough, but also a symbol of American military might at the turn of the 20th and 21st centuries. The production of the B-2 Spirit began not with the manufacturing of individual parts, but with the creation of a completely new industrial ecosystem capable of meeting the unique requirements for technology, materials, and assembly precision. The first and most important stage was the organization of the production base and the development of tools that did not exist before. After the design phase was completed, Northrop Grumman, as the prime contractor, invested over $1,200,000 in creating a specialized integrated composites center in Pico Rivera, California. For this, a former Ford auto plant was repurposed, turning it into one of the world's largest composite manufacturing centers. The production of the B-2 required the development of not only new materials, but also special tools, software, testing laboratories, and automated production systems. At this stage, the following were created: unique molds and tooling for forming large composite panels, automated lines for laying carbon fiber, computerized systems for cutting and shaping parts, and autoclaves for heat-treating composites at a temperature of about 350 degrees Fahrenheit and a pressure of 100 psi. The production of the B-2 began with digital modeling. Engineers created three-dimensional CAD models and then directly manufactured production tools from them, bypassing traditional mock-ups. This allowed for achieving unprecedented accuracy. Even microscopic deviations could affect the aircraft's stealth characteristics. In parallel, a complex network of contractors and suppliers was formed. Over 6,000 companies and 40,000 workers from 46 states of the US were involved in manufacturing components. Boeing was responsible for manufacturing the outer wing sections, Vought aircraft for numerous composite elements, Hughes for radar systems, and General Electric for the engines. Only after the creation of this entire infrastructure did the direct manufacturing of parts, their processing, quality control, and subsequent assembly of the aircraft at the main plant in Palmdale, California, begin. Thus, the production of the B-2 Spirit started with large-scale preparation of the production environment, engineering innovations, and the development of new technologies, which made the creation of this unique aircraft possible. After the large-scale preparation of the production base, the creation of unique tools, and the establishment of material supply chains, the direct manufacturing process of the B-2 Spirit began. Events then unfolded in several key stages, each requiring engineering precision and strict coordination among thousands of specialists and hundreds of contractors. Manufacturing of the main fuselage and wing sections. The manufacturing of the main fuselage and wing sections of the B-2 Spirit began with the production of the world's largest composite aviation parts at that time. The central part with the crew cabin was manufactured by Northrop Grumman, while Boeing made the 65-foot-long outer wing sections and the 50-foot-long aft section. The slightest deviations could affect the B-2's radar cross-section. In total, over 10,000 composite components were manufactured for one aircraft, using the latest automation and quality control technologies of that time. The precision assembly of the B-2 Spirit is a true engineering feat that unfolded in huge hangars specially created for this project. The assembly of the main sections took place on massive jigs, special platforms that occupied an area comparable to a football field. Here, hundreds of engineers, assemblers, and quality controllers worked simultaneously, each responsible for their narrow stage. Thanks to three-dimensional CAD modeling, all parts fit together perfectly. During assembly, laser measurement systems were used, which allowed for tracking accuracy down to thousandths of an inch. Even microscopic deviations could disrupt the aerodynamics or reduce the effectiveness of the stealth coating. Every joint seam was checked several times, and after connecting the sections, it was manually sealed with special materials to ensure airtightness and invisibility. The scale of the assembly was impressive. Just the central fuselage section required over 1,000 hours of labor, and the total assembly cycle for one aircraft took more than a year. All stages were accompanied by multi-level quality control, from geometry to electromagnetic compatibility. It was thanks to such attention to detail that the B-2 Spirit became a benchmark of precision and technological excellence in world aviation. After assembling the main structure, the integration of systems began. Electronics, hydraulics, fuel tanks, engines, flight control systems, radar complexes, and so on. Many subsystems had to be redesigned and adapted to the unique requirements of the stealth architecture. For example, placing the engines inside the wing to reduce infrared radiation. One of the most complex stages was the application of a multi-layer radar absorbent coating. The process took place in special hangars with a controlled microclimate. Each layer was applied by hand and then checked for defects that could increase radar cross-section. After completing the assembly and integration of all systems, the aircraft underwent multi-level tests, static and dynamic structural tests, checks of all systems operation, flight tests in various modes, and special radar cross-section tests. Any identified deficiencies were eliminated, and individual nodes could be reworked or even manufactured anew. After all tests were completed, the aircraft was officially handed over to the U.S. Air Force. In parallel, crews were trained, undergoing specialized training on simulators and in real flights. After the production of the B-2 Spirit ended in 2000, these unique aircraft did not become museum exhibits. On the contrary, they remain at the forefront of technological progress thanks to constant improvement. The U.S. Air Force is investing billions of dollars in modernizing each of the existing B-2s to ensure they meet current and future challenges. One of the main areas of modernization is updating the onboard control systems. Outdated analog instruments are gradually being replaced with modern digital interfaces, which increases reliability, convenience for the crew, and allows for the quick integration of new functions. The crew cabin has been equipped with multifunctional displays, and the flight control system has received new software that provides even greater stability and precision in controlling the flying wing. Every year, over 300 million electric motors are manufactured worldwide, from miniature ones that spin coolers in laptops to giants that power trains, factory lines, and mine elevators. And each one of them is not just a coil of wires and iron, but a complex system of dozens of precisely calibrated parts. How is the heart of a machine born? Why is winding similar to weaving and balancing to jewelry making? And how does one spark power a rotation that will last for thousands of hours? Let's take a look behind the scenes of one of the greatest technical processes, the creation of an electric motor. Inside every electric motor is a true mechanical electrical universe. The main components of a motor are the stator, rotor, shaft, bearings, housing, as well as a cooling system and terminal box. The stator is the stationary part, located in a circle inside the housing. It's what creates the magnetic field that makes the rotor spin. Inside the stator is a core made of layers of thin electrical steel, which reduces losses from eddy currents. In the slots of the core is a winding of copper wire, connected in a special way to create a rotating magnetic field. The rotor is the moving part inside the stator. It either has its own winding or is made in the form of a squirrel cage. Aluminum bars cast into a steel core, which form closed current loops. When the stator's magnetic field interacts with the rotor, it starts to rotate. The shaft is a rod that passes through the rotor and extends outside the housing. It's on this shaft that pulleys, impellers, reducers, or other drives are mounted. It transmits rotation to the mechanisms. The shaft must be precisely centered. Otherwise, the motor will vibrate and wear out quickly. Bearings, usually two, one at each end of the shaft. They ensure smooth rotation with minimal friction. For reliability, they are lubricated with special greases or are sealed. The housing protects the internal elements from dust, moisture, and mechanical damage. It often has fins for heat dissipation or even a fan. The material is cast aluminum or cast iron, depending on the power and purpose of the motor. The cooling system, most often it's simple air cooling, a fan on the shaft drives air flows through the housing. In large industrial motors, liquid cooling or external air circulation through special channels is used. The terminal box is on the outside of the housing. This is where the power cables are connected to the stator winding. Inside, contacts, clamping screws, and sometimes temperature sensors. In the depths of the factory, in a workshop that smells of varnish, metallic dust, and warm insulation, stands a giant stator. A stationary ring with slots around its circumference. This is its core, made of thin steel sheets, tightly pressed together. In each slot of this ring will lie copper wire, carefully laid, loop by loop, turn by turn, because whether the motor will rotate at all depends on this. Before starting the winding, the stator frame is thoroughly prepared. The slots are lined with special insulating liners, like nests for the wire. These are materials that withstand high temperatures, vibrations, and electrical loads. And only when they are sure that the insulation is perfect, the winding machine is started. The machine, resembling a giant spool that unwinds copper wire from a bobbin, wraps it around guides and lays it in the slots. Everything is automated, but under the supervision of a specialist. One sharp movement, and the wire could lay with a kink or snag the insulation. And that's a potential short circuit. For powerful or non-standard motors, winding is done by hand. A worker inserts the wire in a loop, pulls it through with a tool, presses it to the bottom of the slot, secures it, and tightens it. The work is similar to weaving, but with shiny copper and immense responsibility. Each coil, and there are dozens of them, must be identical, symmetrical, and correctly oriented. After the first layer of winding is completed, interphase insulation is laid, and then the second layer is placed. The wire forms closed loops, phases, which are then connected in a star or delta configuration, depending on the motor's setup. Then, the wires are secured with strings or plastic fasteners, the tension and geometry are checked, and if necessary, adjusted by hand. And finally, impregnation with varnish or epoxy resin, so that all this doesn't shift even a micron under vibration and temperature under load. If the stator is the skeleton, then the rotor is the muscle. It moves, rotates, creates torque. It's not visible when the motor is running, but it's what drives everything, from a fan to a train. At the core of the rotor is a steel shaft, long and powerful. Around it, the core is mounted, a set of thin electrical steel sheets stacked into a cylinder. The sheets have slots. These are for the conductors. This is where the most interesting part begins, creating the winding that will make the rotor come alive. One of the most common options is the squirrel cage. Aluminum or copper bars are inserted into the slots, and both ends are cast into rings, like a hoop around a cage. This creates a closed current loop. Such a design doesn't need to be connected directly. Current is induced inside automatically as soon as the motor starts. It's a simple, reliable, and mass-produced option for industry. But if the motor is more complex, more powerful, then classic windings are used. A worker manually lays copper wire in each slot, carefully tightening it, bending it at an angle. Here, symmetry, precise geometry of the turns, and perfect insulation are important. The wire must lie right, not touching the metal anywhere, not crossing over, not being too tight or too loose. A mistake, and the motor will overheat or fail. The rotor windings are then connected in a specific sequence: star, delta, or another type of connection. Everything is secured, insulated, and sometimes varnished. The insulated ends are led out to slip rings or brush assemblies, depending on the design. After this, the rotor is balanced, as it has to rotate at speeds of thousands of revolutions per minute. Any extra 100 grams on the edge, and everything will vibrate, hum, and heat up. The result? A compact, shiny cylinder with windings of copper wire or closed bars. It will be inserted into the stator, and the magic of converting electricity into motion will become possible. It all starts with checking dimensions and tolerances. The gap between the rotor and the stator, the so-called air gap, must be very small. If it's too narrow, friction will occur. If it's too wide, the magnetic field will be weak, and the motor will lose efficiency. The rotor is mounted inside the stator via bearing assemblies. Sometimes special guides or hydraulic presses are used for this. The rotor shaft must rotate perfectly straight, otherwise everything will vibrate or break down within a week. At the ends of the rotor shaft, sleeve or rolling bearings are installed. They allow the rotor to rotate without friction. The bearings are placed in so-called end shields, which are then attached to the motor housing. All surfaces are pre-lubricated with special greases to ensure durability. The ends of the stator and, if necessary, rotor windings are led out to the terminal box. Here they will be connected in the required circuit, star, delta, or another. In complex motors, temperature sensors are installed to detect overheating before a failure occurs. The motor is now assembled, stator and rotor in the housing, wires connected, bearings in place. But it's too early to start it. First, varnishing, drying, balancing, and testing, all like a ritual before the birth of a real machine's heart. In a spacious room with a specific smell of epoxy resin, the stator windings, and sometimes the rotor, are coated with electrical insulating varnish. This isn't just for dust protection. The varnish strengthens the structure, secures the wires so they don't vibrate at high speeds, and prevents moisture penetration. Application is either by dipping in a bath or by spraying. The motor is completely submerged in a tank of varnish, then removed and left to drain off the excess. Next is drying in a thermal chamber at a temperature of 250 to 300 degrees Fahrenheit. This stage resembles baking. The varnish polymerizes and forms a hard protective film. After varnishing, the most sensitive stage, the motor is installed on a balancing stand. The system is like a huge record player. The motor rotates at high speed, and sensors detect the slightest deviations. Even a few grams of excess mass on the rotor can cause vibration that will destroy the bearings, shorten the service life significantly, or even ruin the motor. To eliminate the imbalance, engineers drill microscopic holes in the heavier part of the rotor, removing excess metal. This is almost a jeweler's craft. The finished motor is sent to the test stand. Here it comes to life for the first time. It's connected to a power supply. Rotations, noise, heat, current consumption are recorded, and efficiency and power are measured. Everything is documented. The motor's passport contains dozens of parameters. If the motor passes all tests, it's packaged, a seal is applied, and an instruction manual is added. And very soon, this motor could be working on a conveyor, in an elevator, or in an electric train, wearing down metal and converting current into motion, without rest for tens of thousands of hours. Every year, over 2 billion feet of rope are produced worldwide. But how does a formless cloud of fibers turn into a lifeline capable of holding a tanker, a crane, or a hurricane? We will dive into the depths of rope manufacturing, where threads become muscles, where spindles spin at insane speeds, and the temperature reaches 450 degrees Fahrenheit. You will see machines that look like steel spiders, weaving ropes with micron precision. And if you watch until the end, you'll learn what one detail can destroy even the strongest rope. It all starts with yarn. Yarn is not just a thread. It's the foundation of almost everything we wear, pull, tie, and hang. It is the beginning of the story of any cable or rope. But even earlier, it's just scattered fibers. Fluff, thin strands, like a spider's web. How does this messy mass turn into a resilient, strong, solid thread? It all begins with preparing the fibers. If it's synthetic, for example, polyester, nylon, polypropylene, it's drawn from a melt, cooled, and cut into uniform lengths. Natural fibers, cotton, wool, linen, hemp, are cleaned, combed, and short fragments are removed. The goal is to obtain a soft, elastic mass in which all fibers run in the same direction. Next comes spinning. This is a true art. The fibers are drawn, thinned, and twisted into a thread. Everything happens on large spindles or rotor machines with incredible precision. The character of the thread depends on the strength of the twist. A weak twist will make it fluffy and soft. A strong one, resilient, almost springy. This is exactly what's needed for ropes. Yarn is often made of several threads. For example, 2 or 3 threads are joined and twisted together again in the opposite direction. This stabilizes the structure and prevents it from unraveling. In thick technical ropes, there can be hundreds of such mini threads. Next comes finishing. We don't see it, but it's important. Anti-static additives, thermal stabilizers, impregnation against moisture or bacteria. The yarn can be heat set, meaning it's heated and cooled under tension, so it remembers its shape. And here it is, the finished yarn. On bobbins, wound into dense cylinders. It can become fabric, or it can become the soul of a rope that will hold a seaport or a boat in a storm. A huge hall with rows of machines that look like mechanical spiders. From the bobbins on the upper tiers, thousands of thin, shiny threads are pulled. They are almost invisible, but create a net in the air, like a spiderweb shimmering under the light. And here the movement begins. Motors hum, spindles come to life. The threads fly off the spools and merge into one common ribbon. They seem to seek each other out, intertwine, embrace, and merge into a strand. The strands rush on, through tension rollers, through guides, until they reach the main part of the machine, the twisting unit. And here everything changes. Huge spindles rotate at an insane speed, so fast that their outlines are invisible. You can only guess the movement by the rhythmic gleam of the metal. The threads begin to twist into strands, like muscles building strength. All this happens in silence, broken only by the sounds of mechanics, a uniform hum, clicking, the rustle of fibers. The newly created rope muscles slowly descend, coiling into a spool. The silence in the workshop is replaced by a hum, resembling the sigh of a huge machine. Thin strands, like streams, converge at the heart of the process, the place where they will become one body. Dozens, even hundreds of threads, each separate, independent. But as soon as they pass through a system of rollers and guides, they become something whole. Because in a rope, everything is decided by balance. If one thread is weaker, it will break under tension. If it's stronger, the tension will be distributed unevenly, and the whole structure will go haywire. Here, everything must be like in a choir, synchronous, coordinated, strong. Next, the spindles. These aren't the small wooden spinners from fairy tales. These are steel giants that rotate at such a speed that they disappear from sight, leaving only a shining halo of motion. The threads fly into them like lightning bolts and come out already twisted, with tension inside, with an internal spiral of strength. One turn, a second, thousands of revolutions per minute. And now, instead of fluffy strands, before us appears a sinew that trembles from tension, like a string. You touch it and hear a ringing sound. You pull it and feel resistance. The rope is formed gradually. First, small threads are twisted into sub-ropes, then several such strands into the core of the rope, and finally, the final twisting of the entire body. And at each of these stages, the angle of rotation, tension, thickness, and viscosity of movement are controlled. The rope must not only be strong, but also predictable, so that it doesn't stretch, doesn't twist inside out, doesn't break at a bend. Another magical thing is the spiral pattern. If you look from the side, each strand lies at an angle, creating a classic spiral. This is the law of engineering. Such a shape evenly distributes the load along the entire length, allowing the rope to work as a single muscle fiber. In a super thick marine rope, there can be 3, 4, or more such strands, and each contains hundreds of threads. In the air, there's a light smell of burning and oil, the rustle of fibers, the whistle of tension. The machines breathe, as if alive, and the rope, still damp, hot from friction, slides down, coiling into rings. It hasn't cooled yet. It still remembers the rotation of the spindles, but it already has shape, resistance, a heart. In factories in the US, where industrial ropes are made for ships, cranes, the military, or oil rigs, heat treatment is a mandatory stage. A rope, often 1 or 2 inches in diameter or more, passes through long heat tunnels, from 12 to 40 feet in length. Inside, the temperature rises to 250 to 320 degrees Fahrenheit, depending on the type of yarn. For heat-resistant synthetic fibers, like polyester or aramid, such as Kevlar, it can be even higher, up to 450 degrees. There's no open flame here, only superheated air and controlled tension. The rope moves slowly. In parallel, it's slightly tensioned. Not to break it, but so the fibers line up and remember their shape. It's similar to how a metal spring is heated and its coils are fixed. Each fiber, like a tiny spiral, acquires a stable state, reduces internal friction, and gets rid of residual deformation. This is heat setting. Without it, the rope behaves like raw dough. It stretches, unravels, twists under load. After, it's already trained how to behave under a weight of several tons. Its length is fixed, its resistance predictable. Sometimes ropes also undergo rapid cooling, meaning they are blasted with cold air or dipped in a bath. This helps freeze the fiber structure, preventing them from spreading out. The contrast, 400 degrees of heat and 50 of cooling, shocks the material and makes it even more resilient. Next, the rope is clamped between hydraulic grips, stretched over tens of feet, and subjected to a load of thousands of pounds. Literally, it's pulled to the limit. Digital sensors show every step of the tension: 2,000 pounds, 5,000 pounds, 10,000 pounds. The heavy silence of the workshop compresses as the rope begins to twitch. Each sample has a durability passport: maximum elongation, breaking point, residual deformation. If a rope fails, it's cut, analyzed, and the cause is studied. But even those that withstand need another layer of protection. Because ahead lies the real world, where water, salt, sun, metal fasteners, oil, and dust await them. Ropes are impregnated with protective compounds. Sometimes it's a polyurethane coating, a thin elastic layer that protects against moisture. Sometimes, ultraviolet stabilizers that prevent degradation under the sun. Some models get an anti-abrasive braid, a dense sheath of nylon or polyester that takes the impacts, friction, and wear. This is especially important for marine ropes. Salt corrodes the fibers, so their surfaces are often treated with special lubricants or waxes. For industrial conditions, chemical resistance to oil products, acids, and alkalis is added. One spool of rope contains from 600 to 1,200 feet. Such heavy ropes are often not wound, but coiled into hanks or onto large drums. Mooring ropes can be made to the required length right away, 50, 75, 100 feet without extra winding. Sometimes removable drums or wheeled winders are used, especially for mobile use, in the military, navy, or rescue services.